Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to do this is the second video for Simple Harmonic Motion. So there's a first video for Simple Harmonic Motion that you need to watch before you watch this one. This one will make 0 sense if you don't go watch the first one, okay? So make sure that you go watch the first one so this one makes sense, but this is part 2 of Simple Harmonic Motion, where now we're looking at 2 different systems to see how to kind of describe how they're going to oscillate, okay? So over here we have a mass spring system. Here we have a pendulum, okay? And again, we want to describe, be able to describe what exactly, describe how they're oscillating, what's making them oscillate, right? And in our first video, when we were talking about simple harmonic motion and oscillation, right? We saw that that velocity, right? Anywhere between these max points, we have an equation that we can write velocity as a function of time, again, on that first video that we talk about. But at max points, where we have max velocity or max acceleration, right? We talked about that in those cases, we know how to write those equations. We derived them in that video. But we know how to write those equations, right? Where we see whether it's velocity max or acceleration max, right? Max acceleration or max velocity. For either one of these situations, it has a lot to do with displacement, which is what, right? A's amplitude or x can be displacement from equilibrium. Amplitude and displacement from equilibrium are the same thing again in that first video. But we see they're all based off omega. So we see that the velocity, the acceleration, right? Or really what's telling us how these things are going to move, the motion of these objects, or how they're going to oscillate, looks like omega, right? Omega is really the key factor here. Okay, omega, which is what we call the angular frequency, right, is really going to describe to us how these things are going to oscillate. So if we need to describe how something's going to oscillate, okay, we know it's going to be based off, one of the things that's going to dictate the way it's going to oscillate is omega, right? The other thing that we know that's going to dictate the way something's going to oscillate is K, this K number, or what we call the wave number. So K will also dictate how something oscillates, okay? So what we want to do is we want to make sure that we can describe an omega, right? And we want to make sure that we're able to describe a K, or a wave number, for each system, because those 2 things, right, when we look at them together, are really describing how these systems are going to oscillate, okay? So let's get started over here, right, when we start talking about a spring, right? Now again, the point of this, right, is to figure out how this thing's, based off how this thing's going to oscillate, we can dictate how fast it's going to move, right? We can see the parts of this, the physical parts of this system that are going to dictate its velocity and dictate its acceleration. Same thing over here. We can see the physical parts of the system that are going to dictate its acceleration and are going to dictate its velocity. Because they're not going to, velocity and acceleration are going to be generally the same, but they're going to be different based off the system, right? Because every system, what causes the thing to oscillate is going to be something different. Okay, so when we're looking over here, right, we tell ourselves, okay, well, I need, right, an omega. What is my omega for a spring system? Well, we can go about and kind of derive omega in a sense, or get a sense of omega by understanding the velocity. And once we can kind of derive the velocity, we can look at the equation and see, maybe we can see how omega fits into that. Okay, so what we do is we look at these systems and we can describe them in terms of energy, right? So no matter whether it's a pendulum or a spring, right, we have at each one of these points, when they're sitting in equilibrium, when they're from max displacement, back to equilibrium, max compression, back to equilibrium, back to max displacement, each one of those points from the first video, that's why you need to watch the first video, right? Each one of those points we can describe, right? They're snapshots that at equilibrium or furthest point from equilibrium, those are points that we can look at for both springs and pendulums, right? And we know that when we're at, so these first two pictures that I have here, both for the spring and for the pendulum, we're just trying to describe what this system looks like at rest. Remember, simple harmonic motion only occurs when something oscillates around an equilibrium point. So when these things sit at rest, we know where their equilibrium point is, right? For a box attached to a spring or any object attached to a spring, equilibrium point is where the spring just sits unstretched. An equilibrium point for a pendulum is where the pendulum just sits straight up and down, just like this, right? It's not at any angle or any on this side or this side. And so when we're at those points, when we're just sitting at rest, obviously velocity is 0, acceleration 0, displacement 0, restoring force is 0, kinetic energy is 0, and potential energy is 0, right? And again, we talked about in the first video, but what causes things to oscillate? A restoring force, right? Something's always pulling these objects back to this equilibrium point, right? And what's causing that? Something that we call the restoring force, right? So restoring forces are trying to restore the objects back to their equilibrium point, but those restoring forces are also the force that's allowing these systems to oscillate. Okay, so that's what FR is here, okay? And then we know that when we pull this box furthest from displacement, right, we want to get this thing moving, we're holding it, well, we let it go, right? But just before it starts to move back there, it's sitting at rest for just a second, we pulled it, right, a certain distance, and we let go of it, and right at that point, the velocity will be 0, but acceleration will be max. Again, go watch the first video, but we know furthest from displacement, acceleration's max and opposite. That's what this picture is trying to show you, that when we're furthest from displacement, restoring forces towards equilibrium, accelerations towards equilibrium, and they're opposite of our displacement. So if our displacement's this way, acceleration, restoring force is this way. If our displacement's this way, then restoring force and acceleration's that way. And again, that's true for both of these. So when we pull this out, let it go, and right before it starts to head back, right, it's going to have max acceleration at that point. It's going to be max displacement from equilibrium. The restoring force will be max. Kinetic energy will be 0 because it's not moving, but it'll also have max elastic potential energy at that point, right? And then once this, right, we're not touching the box anymore, so the box is going to move, right? It's going to start to oscillate, kind of jiggle back and forth like this, right? And so when it comes back to equilibrium point, again, in the first video, we said that when these things return to equilibrium point, they'll be moving at max velocity. And I just remembered here, I apologize that I did not come over to the pendulum. So we can see whether we pull the spring furthest from displacement or we pull the pendulum furthest from displacement, the same things are true, right? So when we're furthest from equilibrium, whether it's a pendulum or a spring, velocity 0, acceleration's max, displacement's max, restoring force is max, kinetic energy is 0, and the elastic potential energy, whether it's gravitational for this or elastic for this, but the potential energy is going to be max. Again, when we're furthest from equilibrium, okay? For both these systems, it doesn't matter. And when both these systems, again, come back to equilibrium, so they were over here, now they move back to equilibrium. When we come to equilibrium for both these systems, we know velocity is going to be max, the acceleration will be 0, the displacement will be 0. Again, that displacement is displacement from equilibrium. So if we're at equilibrium, displacement 0. The restoring force is going to be 0. The kinetic energy will be max because if velocity is max, kinetic energy will be max, and the potential energy will be 0 at that point. If kinetic energy is max, remember potential energy must have converted all the way into kinetic, and that's what's happening here. So potential energy better be 0 when kinetic energy is max. Okay? And again, this is at equilibrium point. Now, these systems then move to this side, right? This one compresses, this thing swings to, the pendulum swings to this side, but right, we were over here, now we came to equilibrium, now we're over here. And we're over here at max displacement from equilibrium again, no matter which one you're looking at, right? This is displacement from equilibrium, okay? This is displacement from equilibrium. Okay, we get the same thing where velocity is 0, because this is a point where they're both going to stop, right? They're going to stop and start to head back this way. So at the point where they stop and get ready to head back this way, their velocity will be 0, but they'll have max acceleration. And if this is playing with you, don't be like, how can you have max acceleration and 0 velocity? Very simple. Very, very, very simple, right? Think about with projectile motion. At the top, right, when I throw this marker up, right, in free fall, at the max height, this marker stops, but the acceleration's max, right? That's why it starts to come back down. So it's having acceleration max and velocity 0 is a normal thing, right? And so we see at these extreme points where they stop, velocity will be 0, but acceleration will be max. If acceleration max, so is that restoring force will be max. And we know when we're have max acceleration, we must be furthest from, or displacement must be furthest from equilibrium, so that'll also be max, right? And if we're stopped, kinetic energy will be 0 at that point, but the potential energy, whether it's elastic potential energy for a pendulum, or elastic potential energy for a spring, or gravitational potential energy for a pendulum, no matter which one, they'll be max when they're furthest from displacement. All right, now these things, they come back to equilibrium, which is really this situation up here, but now we're moving, right? Here, right here. Right, this one was the one where we're stopped, but, right? When we come back to equilibrium, when we go from here to equilibrium, it's really just this situation again, right? So when we're over here, but come back to equilibrium for both these systems, we know the velocity will be max at equilibrium, displacement from equilibrium will be 0, acceleration 0, restoring force is 0 at equilibrium, but kinetic energy is max, velocity is max, so kinetic energy must be max. Potential energy at that point is 0, okay? And then again, it displaces again furthest from equilibrium. The same things are true. Velocity will be 0 when it's furthest from equilibrium. Acceleration, restoring force will be max. Displacement will be max. Kinetic energy will be 0, but potential energy will be max for both these systems, okay? And you can just watch this, right? These are the resting point. So from this point all the way down, you can just watch this thing oscillate, right? We come back to this point down here. This thing oscillates and comes back to this original picture. Okay, so you want to be able to describe these things in terms of the potential energy with these, because you've got to be able to describe them in terms of their potential energy, but you also can describe these things just in terms of force, right? If I wanted to write a free body diagram based off displacement from equilibrium, this is what it would look like, right? When I'm furthest from equilibrium, the net force will be pointed towards the equilibrium point, because that's, right, or the restoring force, right? Because that's what the restoring force is trying to do, is restore it back to its original position, which is at that equilibrium point. Acceleration, restoring force, right? They're proportional, so they'll always be in the same direction, right? So restoring force is toward equilibrium, so will acceleration, right? And that restoring force is equal to negative kx. That's what we know from Hooke's law, okay? And so what we know is that restoring force is a net force, so it's going to be equal to ma. And then we also know that restoring force is equal to negative kx, so we can write a Newton law that says that the kx, right, or this restoring force, is equal to mass times acceleration, okay? And I got rid of the sign there because these are going to be the same. You don't need the sign there. But that's the Newton equation to describe this situation if we needed to, okay? So, what do? So we go ahead and we start to, like I said, the thing that we need to know, because we want to be able to describe how this thing's oscillating, we know that omega is the thing we need. So we can use this idea of conservation of energy, where the max kinetic energy transfers into the max potential energy, which transfers back into the max kinetic energy, right? Just keeps going back and forth like this, right? We can use this idea to derive an omega, kind of like, not directly, but you'll see how we do it. We can see how to get omega. So again, you start with conservation of energy, as we can. We know that kinetic energy max is described as 1/2 mv squared. The potential energy max is going to be Hooke's, right? The Hooke's law, we know that potential energy, if you forgot, is equal to 1/2 kx squared in terms of elastic potential energy, and that's the type of potential energy that's here. So that's the potential energy we make it equal to, okay? And the next thing we do is we cancel out the 1/2, so those go away, and we get this equation. Now again, we're going to try to solve this equation for velocity, because if we solve for velocity, we can indirectly see omega, and that's the idea. Another way to do it, we could have done it, and I'll show you, is we could have solved this equation for A, and we would have solved something as well. Okay, so either way, depending on how you want to get omega, the point is that you need a new omega. Omega is the thing that's going to describe what's going on here. Okay, so that's what we're doing. After the 1/2s cancel out, we want to solve this equation for velocity, because like I said, when we solve this equation for velocity, we can indirectly get omega. So when we solve this equation for velocity, right, this is velocity squared, what ends up happening is to get rid of the velocity squared, we have to, m's going to come under k, and we're going to square root this whole side, and when we square root this whole side, since x is squared, x will lose the squared and come out to the side, so this is multiplying by the square root of km. Now k over m, right, m is just going to come under k over here, okay, that's how we get k over m, but since k over m isn't squared, when we do the square root of this whole side, since we have to, it's v squared, the x will lose the squared and become independent, but km has to keep the square root over it. Okay, that's the math there. Now, what's this telling us? Well, if we look at our original equation for velocity, it's telling us something. This x, right, is displacement from equilibrium, and that's what this x was in terms of our velocity equation for a simple harmonic motion. And if that's true, that makes this term right here, this km, is going to be omega. So that's how we indirectly find it. We say, okay, well, if we know for simple harmonic motion, velocity is equal to omega times x, we just derive this equation where we have some value times x. Well, these are the same. X is distance from displacement. We know that in this equation. And if that's true, then this square root k over m must be omega. That's what I'm trying to say here, right? And no matter how we write it, either in terms of x or in terms of amplitude, right? This equation is the same way. We know x, right? X max is equal to a, so x can be written in terms of x or a, right? But either way, no matter how you write it, right? We know that the square root k over m is the omega, right? And this x is displacement, right? It's displacement from equilibrium, no matter if we talk about it in terms of x or amplitude, all right? Now, if you're saying, Carl, what's the other way you could have done it? Right here, okay? We could have solved this equation, this kx. We could have solved it for acceleration, okay? Give me a little more room here. So we could have solved it for acceleration. And when we do that, sorry, that looks like kinetic energy. When we do that, right, m's going to go under k, and x is going to stay put. So when I solve for a, m is going to come over here and go underneath, right? And so this is acceleration from this equation. Well, what else do we see? Again, indirectly, we're indirectly seeing something that, right, this omega, if this is omega squared, right, this must be omega if this is x, but since this is omega squared, right, this must have a square root over it for it to go away, all right? If that's a little tricky for you to see that, don't worry about it. That's why we don't do it that way, okay? We don't do it that way. It's another way to do it, but we don't do it that way. What we typically do is we indirectly find omega by finding the velocity from the kinetic energy. We do the same thing over here, okay? So by using kinetic and potential energy, we solve for velocity. By solving for velocity and comparing it to our simple harmonic equation for velocity, we see that the square root k over m is the omega, and this x is again what we've always called it. This x in here is displacement from equilibrium, so it doesn't change in this equation. So that's how we know what omega is. That's how we got omega, by comparing it to the simple harmonic equation and saying omega, this square k over m must be omega. It has to be, based off the way these equations are written, okay? So we found omega. Omega for a spring system is k, which is what we call, right? K is, in this case, we call k the spring constant, right? But it's also, can be called the wave number. And m is mass, right? So we see that the thing that dictates how these mass springs are going to oscillate, that's what this is telling us. What dictates how it's going to oscillate? K, which is a spring constant, so K is how stiff the spring is, right? And the mass, how big of a mass we attach to the spring. Those two things are going to dictate omega, or the angular frequency, how it oscillates, right? Okay, because that's what we're trying to say. We needed a new omega. Why? Because omega tells us what properties make this thing oscillate. So for a spring system, by finding omega, we found out that a spring system oscillates based off how stiff the spring is, which is K, and the mass attached to that spring. Okay? Now, since we have omega, we can get a max acceleration equation by plugging omega into our max acceleration equation that we got from our simple harmonic motion graphs. Now again, you need to watch the first video if you want to know where these came from. That's what the first video is about. So taking these equations from the first video, we want to just, now that we have an omega, swap omega in, because since omega is describing how this thing's oscillating, it's not only describing velocity, it will also describe its change in motion, its acceleration. So when we take this omega we just derived and put it in here, since it's omega squared, that square root's going to go away, and we're going to end up with acceleration max equal to k over m times x. Again, x is just displacement from acceleration, and x can be wrote in terms of amplitude. So either way, no matter how you write it, k over m times x, which is displacement, or k over m times amplitude, which again, amplitude and displacement are the same thing. Either way, that's the equation. So if you want to know the value of max acceleration, there's like, what's the max acceleration, right? When we have max acceleration, what's the value here? Well, if you divide the spring constant by mass and multiply it by how far you displaced it, you'll get the acceleration at that point, okay? Whatever the displacement is, x is the displacement can be anything, right? But we're considering the max displacement, so wherever it stops, that's the max displacement, so x would be that point, okay? Now, since we're able to both describe, we found a new omega that describes velocity and acceleration, we can also use that omega to derive a period. And what period is it just, period is just how long it takes. So t, it's a big T, but T stands for time in here. The units for period are seconds. We're finding time here. It's not a, we use a weird thing, but that's all this is, okay? We call it a weird thing, we could just call it time, but it's not. It's period. And so why do we call it something specific? Because of the period is how long, the seconds, the time it takes to make one full revolution or one full oscillation, right? So one full oscillation for a box is coming out here, coming back to equilibrium, coming here, and then coming back to equilibrium, okay? That's one full oscillation. If you just come from here, out, and then back to equilibrium, that's only half an oscillation. You have to come out, come back, squish, and come back for there to be a full oscillation. And again, this is in the first video we talk about that. It's the same thing for a pendulum, okay? When I start here and I go here and come back to equilibrium, that's only half, okay? If I want to make a full oscillate, right? If I want my oscillation to be full, I have to swing here, come back to equilibrium, then swing here and come back to equilibrium. That's one full cycle, okay? That's what we call one full cycle. So if I'm a pendulum and I come from here and come, so I start here, I come to here and come back here, that's only half a cycle. For there to be a full cycle, in order to get the period, and a period's a full cycle, the time it takes for a full cycle, I have to start here, come here, come here, come here, and now I've made a full cycle. For the box spring, I'm going to start right here. I got to come here, come back here, then go here, and then come back to equilibrium. So you come back to equilibrium twice. Well, you start at equilibrium, right? And you come back to equilibrium twice, or you end up at equilibrium for one full oscillation. Okay, so keep that in mind, right? And if you don't remember, I'll do it one more time over here, right? Where you start at equilibrium, you go away from equilibrium, right? And you come back. So if this is equilibrium point, you leave equilibrium, right? So if this is the pendulum, this part is this, then it's going to come back to equilibrium, then it's going to go away from equilibrium, away from equilibrium, then it's going to come back to equilibrium. That's one full wavelength, that's what we call, or one full cycle. To get the time that it takes to make that cycle, that's what we call the period. Okay, and we can derive that equation because we know omega is equal to 2 pi over the period, and we also know omega for this system is equal to the square root of km. So when we make those equal to each other, we can solve this equation for t, or for period. Now when we do that, keep in mind that km is going to swap places with t. So when km comes down here, we need to flop it. It needs to swap, right? Because when km, we'll do it over here, when km comes into this equation, okay, we put it in here, right? Km's going to come down, t's going to come up. So it looks weird at first. T is equal to 2 pi square root k over m, but we can't leave it like this. So what happens is km flop. So the 2 pi stays, but km just flops. Oops. The square root of km just flops. So this is what, oops, I didn't do it. There we go. Right, where m comes on top, k goes on the bottom. It's just because the math, when this comes up, because this is a fraction, we don't want it. So when we end up doing it, right, when this comes up, m and k switch places. So that's why m is on the top here, because our omega, m is on the bottom, right? But when we get the period, m is on top, and it's just because the flop of the math. Just keep that in mind of what we're doing. I just showed you, okay? Because the same thing happens over here. All right. So, just like over here we needed an omega, over here we need a new omega, okay? We need an omega that's going to describe how this thing oscillates, right? But we also know, right, so we know, okay, need an omega, omega tells us how these things oscillate. But we also know that in terms of the restoring force, this k over here was the spring constant. It made sense when we were talking about with the pendulum, right? But over here, k, right, to have this k, well, this isn't a spring, this is a rope, right? It's a rope attached to a ball, right? So, or a weight, something at the end, right? It doesn't have to be a ball. But, so this k, right, isn't what it is over here. Over here, this k is the stiffness of the spring. Now, this k is still appropriate. And why it gets this new number, this wave number, we don't call it a spring constant anymore, is because k is still also dictating how this thing oscillates, right? But we gotta find a new way to describe k because we can't describe it as a spring constant. So before we start to derive omega, right, we know that we need a k, a new k, because the way that we describe a k right now in this equation doesn't make any sense. So we want to use, we're saying to ourselves, hey, we know omega in a sense, but the only way that I can get omega is to get a new k. So we got to first derive a new k, and that's what we do. So in order to do that, we got to start with the free body diagram. Now this free body diagram is a little weird because before, when we drew these equations, right, like in the previous chapters, right, if we had a ball like this, what we did is we said mg was down, and then what did we do? We called that tension, right? The force was tension, and then what we did is we turned tension into components. We gave tension, since tension is the force at an angle here, we gave tension components, okay? And then we derived things. Well, here we switched them, and again, the reason why we did this is because the coordinate system we had looked like this, okay? But for this one, we align the coordinate system with the rope. So this is negative y over here. And when we do that, when we align the coordinate system with the rope, now the tension, the rope doesn't have any components because the tension's aligning with our coordinate system. But mg now gets components. If tension's aligning, just it doesn't mean that angle goes away. It's just now we associate that angle with mg. So instead of right, because if we're aligning our system like this, right, that means mg over here, mg sat straight up with the y, right? But here mg sits down, but y sits at an angle. So just by writing our component or our dimensions this way, we can make mg sit at an angle rather than tension. So that's the first important thing that we have to do here to derive this, is we want mg to have components. Why? Because when we give mg components, we can see the restoring force here. What's causing this pendulum to come back to equilibrium? That's that, right? We want to know what it is, and when we put when we give mg components, we see that the mg cosine is balancing out tension, right? So these have two jobs. Remember, when we separate into components, these forces are independent. They're doing two different things. We can see mg's cosine, right, is this. It's balancing out, right? Tension's this way. It's balancing out tension, okay? So we see it's this mg sine theta that's pointed towards the equilibrium, and it's the mg sine theta that is the restoring force here, okay? We also know that the restoring force is a net force, right? There's acceleration there, right? That's the direction of the net force. Acceleration is also going to be in the same direction, right? And so because this is true, and we know that the net force can also be equal to kx, because of all these things, we can set, right, mg sine theta equal to kx. As restoring force is equal to mg sine theta, it's equal to ma is equal to kx. So ma and kx are equal to each other. If ma is equal to fr and fr is equal to this, and this can sub in for here, and we get mg sine theta is equal to kx. That's how we end up with that initial equation, okay? Now we use that equation to get a new k, all right? So we start with mg sine theta is equal to kx. Again, you know why, all right? Now the next thing we do is we use something called a small angle approximation, because sine theta, let's say we don't know that theta, but let's say we only, right, we just did a small, you know, it's not a big, if this is, let me make sure I can do this, right? Now I'll have to use this. So let's say that this is my arm's equilibrium point, this is going to be the pendulum. Now, if I do a huge angle, right, so the angle right here, right, that's a huge angle. You can't use small approximation, what we're about to do for this. But if we just displace this thing, just a small point, so the angle, right, when we displace it is only going to be very small, very small. It's not a large one. It's a very small angle. When we displace this just a small bit, that theta, we can use small angle approximation to derive that theta, and we can use sine theta in order to derive that small angle approximation. So we know in order to get like that theta right there, right, can be found in terms of opposite and the hypotenuse, right? We know sine theta is equal to opposite over hypotenuse, right? Well, in this case, the opposite of that angle is the displacement from equilibrium, and the hypotenuse for that angle is the length of the rope. So we can write sine theta opposite over hypotenuse in terms of sine theta of x over L. Now, because this is a small angle approximation, we can now take that sine theta and totally replace it with x over L. Now, we can't do this all the time, only for very small angles. So only if we displace it a very small bit will this work. If they're large displacement angles, this doesn't work. Okay, but for very small, sine theta will be equal to x over L. So we can totally replace sine theta. Since they're equal, we can replace sine theta with x over L. That's the first thing that we do, okay? After we do that, now we can see that there's x's on both sides. We cancel those x's, and once we do that, we get our k, the k we were looking for. We knew we needed a k. There's our new k. So a k for a mass spring system is mg over L, where L is the length of the rope that the pendulum's attached to, okay? Now that we have k, we can use it, hopefully, to find omega, all right? But first, we have to do the same thing we did over here and find omega in terms of velocity. So just like over here, when we use the conservation of energy, we do the same thing, but it works the same way, right? We saw that, this says EL, and that should say G. Well, actually it should say EL, I apologize about that. It's about to make a mistake, sorry about that. Okay, so we know, right, from this system that this thing just goes from max potential energy to max kinetic energy, right, to max potential energy to max kinetic energy. We know this, right? This is something that we know. And so, because of this, this situation stands true, just like over here. The K max will go into the potential energy max. That's what I mean to write there. Sorry, I meant to write max. I knew it was missing something, right? So this K max is going to go into this potential energy max, okay? And it's going to go back and forth. When potential energy is max, and all that potential energy is going to convert into K. That's what we see here. So we can write this equation, right? Then we want to expand it out, right? Where K max is equal to 1/2 V squared, and the potential energy, right, for Hooke's law, that's where this is coming from, is equal to 1/2 kx squared. Okay, again, we're just trying to derive a velocity equation so that we can indirectly get an omega and then hopefully fit our k in, okay? So the next thing that we do is we cancel out these 1/2s, right? So when these 1/2s cancel out, all that's left is mv squared and kx squared, right? And the next thing that we want to do is we want to change that k. Since k isn't the spring constant, but k is now mg over L, we need to replace that k with mg over L. So all that happened in this next step is k turned into mg over L with that x squared stayed and v squared stayed, okay? Now, once we have this situation, we see that mass is on both sides of the equation, so mass can cancel. And when we cancel mass, we end up with v squared equals to gl times x squared, all right? And then just over here, right, like we did over here, to get rid of the squared, we have to square root both sides. And when we square root both sides, we end up seeing that the x squared will just lose its x, or lose its squared, right? So this will just be multiplied by the square root of GL. Now remember, we have to square root both sides. When we square root both sides, the v will lose its squared, the x will lose its squared, but g over L, since it's not squared, will keep the square root. So when we do this, just like we did over there, we indirectly found omega. We see that omega for now a pendulum is g over L, the square root of g over L. Okay, and then x, right, is just displacement. Again, where's that coming from? The general equation for max velocity for a simple harmonic motion. We compare this equation to it. We see, well, if these x's are the same, then whatever's here must be omega, right? And whatever's here, what's here is g, square root g over L. For that one, what's here? Square root, or square root of k over m. Okay? So that's how we get that. So we know omega now. We got our omega by finding the velocity, and omega for a pendulum is square root of g over L. What does that mean? That means the things that dictate how this thing's going to oscillate is the gravity that the pendulum's interacting with and the length of the rope. What is that telling you? This is actually cool. That has nothing to do with the mass at the end. We could make this mass at the end of the pendulum 200 pounds and then have another pendulum where the mass is only 1 ounce, and they would oscillate the same if their ropes are the same length and they're both on Earth. Another cool thing about this is that we can use, that's what you can use this period for, is we can use this period to find G, all kinds of stuff. We'll talk about that here in a second, okay? So, since now that we have our new omega, which is square root G over L, these are the things that dictate how a pendulum is going to oscillate, the gravity and the length of the pendulum, right? We can take that omega and now put it into, right, we know how acceleration, max acceleration is written, so we can place that omega in here, and since this is omega squared, that square root's going to disappear, so acceleration max, right? The max acceleration for a pendulum can be written like this, G over L times displacement, right? G over L, right, gravity, over the length of the pendulum times x. And what's x again? X is the distance, how far you are, how far you're displaced from equilibrium, right? And we know x, displacement from equilibrium, and the amplitude on the graph, they're equal to each other, so you can write this either way. It's the amplitude or the displacement, right? But the max acceleration for a pendulum is based off the gravity and length of the pendulum, nothing more, okay? And then, like we want to do, we want to also derive the period, because we want to see how long it takes to make one full cycle or one full oscillation. So we do the same thing. Omega is equal to these two things. And since they're equal to these two things, we can set the equations equal to each other. 2 pi over t equals the square root g over L. And then again, we solve for t. What's t again? Period. What's the units for period? Seconds. So this is the time it takes for one cycle. That's what a period is. One full, oh, I erased it, but one full cycle. Don't forget that. One full oscillation, This is the time it takes to do it, okay? And we see that the time, right, is 2 pi over, times the square root of L over G. Now keep in mind, it's written G over L, but they flip for the same reason that they flipped over here, okay? So this is it. This is the end of the video. Okay, make sure you understand this. Go back and watch it a billion times. Understand these free body diagrams. Understanding over here, we have to derive a new K. Since this isn't a spring, we can't describe K like we do over here. Over here, K is a spring constant. Over here, K is this new thing we call a wave number, right? But K is going to have a new value because this is a new system. So the first thing that we did is we had to just derive a new K where we didn't have to do that over here. Once we had a new K, we then used that K to derive a velocity. Where over here, we used that K as a spring constant to derive velocity, okay? Once we had velocity, we knew what omega was going to be, because the way that the simple harmonic equation is written, we knew that omega must be G over L because this X is equal to the same thing there. And once we knew that, we knew omega, then we could put omega and replace it wherever we needed to get the rest of the system and describe the rest of the system, how it's going to work. All right. I hope this was helpful. I'm super proud of you. Again, you've made it very far. I just, I can't tell you how proud I am. Okay, that who cares what your grade is? Who cares what's going on? You made it this far. All right, and I hope you're proud of yourself because I'm proud of you. All right, I'm super proud of you. Keep up the good work. Don't give up on your dream. Don't let physics hold you back from your dream. Get there, okay? This shouldn't hold you back, all right? I'm super proud of you. Make sure you watch this a billion times to understand it. Free body diagrams, I want to do all of it. I'll see you on the next video.